Welcome, my friends! I am so excited because in this video, we get to talk about probability as it relates to two events. And this is where the problems really start to get fun and interesting. So let's go ahead and get started. So believe it or not, there actually ends up being 4 different ways you can ask a probability as it relates to two events. One thing you could ask is, what is the probability that either your first event A or your second event B occurs? And we call that the probability of A or B. We could also ask the probability that both A and B occur together, and we call that the probability of A and B. And then we could ask about the probability that one event occurs given or assuming that another event is also going to occur. And that would be something like the probability that event A occurs given that B occurs, or the other way around, the probability that event B occurs given that A occurs. We read the vertical line here as given or conditional upon. These last 2 probabilities are what we call conditional probabilities, the chance that one event occurs given or conditional upon another event occurring. It's important to remember for conditional probabilities that the event you're trying to find the probability for is listed first, and the event that you are conditioned upon is listed second. So A given B is saying, what is the chance that event A happens given or assuming that event B is going to happen, or vice versa. The chance that event B happens given that event A has happened or is going to happen. Note that the order does matter for conditional probabilities, but it doesn't matter for the or and probabilities. So for example, A or B would be the same as B or A and B would be the same as B and A, but A given B is not the same as B given A. You'd be finding the probability of a different event. When considering the probability of A and B, we must consider whether or not those 2 events are independent or dependent. So here is an example to help exemplify what that means. Let's say we have the 3 events, event A, getting an A on the test, event B, flipping heads on a coin before you take the test, and event C, getting a bad night of sleep the night before the test. 2 events are independent if the occurrence of one event does not change the probability that the second event occurs, such as events A and B. It doesn't matter if you flip heads on the coin before the test, that's not really going to impact the chance that you get an A. So therefore we would say that events A and B are independent. You could also say that events B and C are most likely independent, but right now I'm focusing on the comparison to event A. 2 events are dependent if the occurrence of one event does change the probability that the second event occurs, such as events A and C. If you get a bad night of sleep the night before a test, that's most likely going to impact your performance on the test, and probably decrease the chance that you get an A. We always must consider whether or not 2 events are independent or dependent when trying to find the probability that both of those 2 events happen together. So let's take a look at the formulas. If A and B are independent events, the probability that both events A and B occur is equal to the probability of A times the probability of B. Let's look at an example. Let's say that A is the event where you get an A on the test. And let's say that we know, based on historical data, that about 20% of students in a class get an A on the test. Let's say that event B is that you flip heads before the test. The probability of B, assuming a fair coin, is going to be 0.5. Since we already said that these are going to be independent events, we can find the probability that both A and B occur, that you both get an A on the test and flip heads before the test, is going to be the product of those 2 probabilities. 0.2 times 0.5, which is equal to 0.1. The probability that you both get an A on the test and flip heads before the test is about 10%. Now what if your 2 events are dependent, meaning the occurrence of one event actually affects the chance that the other event occurs? Well, if your 2 events are dependent, it becomes a little bit more complicated. There are actually 2 different formulas that can help you calculate the probability of A and B. You can either take the probability of A and multiply it by the probability that B happens given that A has happened or is going to happen, or do it the other way around, the probability of B times the probability of A given B. You should use the formula that works with the values given in your problem. So if you have the chance of A and the chance of B given A, then you should use the first formula. And if you have the chance of B and the chance of A given B, then you should use the second formula. Let's look at an example. Let's say that the event C is that you get a bad night of sleep the night before the test. Let's say that the chance of this happening is 15%. Let's also say that the chance that you get an A on the test, given that you did not sleep well the night before the test, is an 8% chance. Notice the difference here. The general chance that anyone gets an A on the test is 20%, but the chance that someone gets an A on the test, given that they have not slept well the night before the test, is only 8%. So not getting a good night of sleep actually changes the probability of A. Therefore, we would say that events A and C are dependent events, because knowing that C happens actually decreases the chance of A. Now, of course, at this point, we don't have the letters A and B, but we can modify either of these formulas to work for the events A and C. The probability of A and C is equal to the probability of C times the probability of A given C. I've just modified this second formula over here and replaced any of the B's with C's. This is the formula we're going to want to use because we have the probability of C and we have the probability of A given C. If we wrote out the formula using this form, we would not have the correct numbers. The probability of C is 0.15 and the probability of A given C is 0.08, so multiplying those together, we get the probability of A and C to be 0.012. There's about a 1.2% chance that you both don't get a good night of sleep the night before the test and then also get an A. Now, one other thing that we might want to do is solve the formula directly for the probability of A given B. So here I have that second formula from the previous slide. Using some algebra, if we divided both sides by the probability of B, we would get that the probability of A given B is equal to the probability of A and B divided by the probability of B. This is the conditional probability formula. Once again, in general, you may need to modify this formula to work for events other than just A and B. In general, the way that I remember this formula is to find the probability of something given something else, you basically just change this given sign to an and that will be your numerator. So instead of A given B, the numerator is A and B. And then you always divide by the event that you were given. So then we divide by, in this case, the probability of B. So let's go ahead and look at an example. Suppose there is a 20% chance a student is a business major, that's going to be event B, and a 15% chance that a student is both a male, event M, and a business major. What is the probability a randomly selected student is male if we know that they are a business major? Now, the first thing you should do whenever you read a probability problem like this is write out the probability statements that go along with each event. Believe me, that's going to save you a lot of work and a lot of issues if you can, correctly identify the events that are kind of going along with some of these numbers. So in this problem, first they give us the chance that a student is a business major. So that is the probability of B. Second, they give us the chance that someone is both male and a business major. So that is the probability of M and B, which is 0.15. Now, the tricky part for some students is identifying this last part, or the probability statement related to this last part. They say, what is the probability a randomly selected student is male if we know that they are a business major? Another way this could have been written is, what's the chance that they are male given they are a business major? So that means that we are trying to find the probability of M given B. Remember, the first event that we write is the event that we're trying to find the probability of. In this case, the chance that someone is male. But we know that this person is going to be a business major. So we are given that they are in event B, or that they are a business major. So once again, kind of modifying this to work for our events that we have. Instead of A and B, we have M and B. So using that kind of a general idea that I talked about earlier, if you want to find the conditional probability, just change the given sign in the middle to an and that's going to be your numerator. So instead of M given B, we have M and B, and then we always divide by our second event, which in this case is B. So we're dividing by the probability of B. And at this point, we have all the numbers we need to plug into the formula. The probability of M and B is 0.15. The probability of B is 0.2. So altogether, the chance that someone is male, given that they are a business major, is a 75% chance. Now, sometimes it might not be that clear whether or not your two events are independent or dependent. And that can make it very difficult to know which formula to use when you're calculating probabilities. Well, it turns out that there is a way to prove that two events are independent. two events A and B are independent if it can be shown that one of the following three conditions are true. And I'll just tell you right now, if one of these conditions is true, the other two will also be true. So one way is to show that the probability of one event given the second event is equal to just the general probability of the first event. And this makes a lot of sense if you understand the notation. This first part is saying what is the chance that event A happens if we know that event B is going to happen. Well, if that's the same thing as the general probability of A, then that's kind of like saying, well, event B didn't really have any impact. The chance of A happening is the same if we know that B is going to happen as if we don't know if B is going to happen, is kind of the one over here, right? So that's one way. If you can show this is the case, then those two events are independent. Or you could just flip it around. You could say the probability of B given A is equal to probability of B. And if that was the case, then your events would be independent. Or if the probability of A and B is equal to the probability of A times the probability of B, which was the formula for independent events, then your two events would also be independent. So once again, these three conditions will either all be true or all be false. So as long as you can show that one of these is true, you can show that your events are independent. Let's look at another example. Suppose a smoothie stand sells a variety of smoothies. The owner knows from his records that 30% of smoothies sold are the strawberry flavor, event S. In general, 40% of all smoothies sold are the large size, event L. But specifically for the strawberry flavor, 60% of smoothies sold are the large size. So once again, the very first thing you should do is write down all of the given information. And at this point, a question has not even been asked. So the first thing they say here is that 30% of these smoothies sold are the strawberry flavor. So that's just the probability of S. They also tell us that 40% of these smoothies are the large size. So that's the probability of L. Now be very careful about this last part. Specifically for the strawberry flavor, or given that we have the strawberry flavor, or conditional on something being the strawberry flavor, 60% sold are the large size. So this is the probability that we have a large size given or conditional on having the strawberry flavor, which is equal to 0.6. So are events S and L independent? Well, we would have to use one of those formulas from the previous slide. And once again, if you kind of understand what is meant by some of this notation, you shouldn't even really need to look back at the formulas, because it should be very apparent to you that these events are not independent. The probability in general that we have a large size ordered is 40%, but the chance that we have a large size ordered given that we have a strawberry smoothie is 60%. So that means that these two events are not independent. These are dependent events. Knowing that we're going to have a strawberry flavor influences the chance that we have a large size. There's a 60% chance of having a large size if it's strawberry versus a, in general, 40% chance of having a large size. So these are not independent events. The probability of L is not equal to the probability of L given S, so these would be dependent events. Next, we are asked to find the probability that a random smoothie sold is both strawberry flavor and large size. So since we said these are not independent events, they are dependent events, and we have to use the dependent event formula. There are two different formulas, but the one that's going to work for us is the probability of S and L is equal to the probability of S times the probability of L given S. The reason why this one works is because we have the probability of S and we have the probability of L given S. If you switched around the S's and the L's to get the other formula, you'd notice that we don't have the correct numbers. So plugging into the formula, the probability of S is 0.3 and the probability of L given S is 0.6. So 0.3 times 0.6 is 0.18. There's an 18% chance that a random smoothie that we select is both strawberry and large. If we know that a large smoothie was ordered, what is the chance that the flavor was strawberry? Once again, be very careful to make sure you identify what question they are asking, or the probability statement associated with the question that is being asked. They are asking for the probability of S given L. If we know that a large smoothie was ordered, it's saying that we are given L, are conditioned on being a large smoothie. And we're asked to find the probability that we have a strawberry. So the chance that we have a strawberry smoothie, given that it is large, is equal to, well, change the given to an and, so that's S and L, and always divide by the second one, which in this case is L. So just plug in the numbers. 0.18 from our previous question divided by 0.4, which was the probability of L, and we get 0.45. If we know that a large smoothie was ordered, the chance that it's strawberry is 45%. Alright, so here is a problem for you to try. So pause the video and give this a shot, and I'll be right back to help you out. Alright, at this point I'm assuming that you have paused the video and given some of this a try. The problem says that 20% of the workers at a company are managers, event M, 40% of all employees have children, event C, and of the managers, 60% have children. And the very first question says, write out the probability statements for the three probabilities that are given. So first they say 20% are managers, so that would be the probability of M. 40% have children, so that's the probability of C. And of the managers, 60% have children. So that's the probability that someone has children given they are a manager, which is 0.6. Are events M and C independent or dependent? Well, in this case, the chance that you have children is a 40% chance, and the chance that you have children given that you're a manager is 60%. So if you are a manager, you are more likely to have children than the general employee. So we would say that those events are dependent, as the probability of C is not equal to the probability of C given M. What is the probability a randomly selected worker is both a manager and has children? So we are being asked for the probability of M and C. And since these are dependent events, we have to use the dependent events formula, which is the probability of M times the probability of C given M. We could have also switched around the C's and the M's in this formula, but we don't have the numbers for that. We had the probability of M and the probability of C given M. So when we multiply those two together, we're going to get 0.12. There is a 12% chance that a randomly selected worker is both a manager and has children. The last problem says, what is the probability an employee is a manager if we know that they have children? And I'm not going to solve this one for you. I will just say that make sure you are writing out the probability statement, and my only hint to you is that this is a conditional probability. Alright, at this point we are ready to talk about events involving A or B. Now note that when we say A or B, there's really three ways that that condition can be satisfied. Only event A could occur, only event B could occur, or both A and B could occur together. So just to give you a little bit of an example here, let's say that I was going to either go for a run or go on a bike ride. So to satisfy the condition of either going for a run or a bike ride, we could either go for a run, go for a bike ride, or both go for a run and a bike ride. Some people might think that this third condition would not be included in the or criteria, but usually it is included. If you do both of those two events, then that is usually considered part of the or. Now, whereas when we talked about and probabilities, we had to consider whether or not the two events were independent or dependent. Now when we have or probabilities, we're going to have to consider whether or not those two events are mutually exclusive. By mutually exclusive, we mean that those events cannot happen at the same time. If two events are mutually exclusive, then the chance that they happen together is going to be 0. An example of that might be the events related to rolling a 6-sided die. So maybe your first event is that you roll a 1, and your second event is that you roll a 2. Those two events would be mutually exclusive. If you're going to roll one die, you're either going to get a 1 or a 2 or something else, right? But you're not going to get both a 1 and a 2 in one roll. So therefore, we would say that those two events are mutually exclusive, and the probability that they happen together is going to be 0. So then we have these so-called addition rules related to or probabilities. The addition rule for mutually exclusive events that cannot happen together is that to find the probability of A or B, all you have to do is add the probability of A and the probability of B together. This sort of parallels the probability of A and B when you had independent events, which was the probability of A times the probability of B. Now, if you have non-mutually exclusive events, events that can happen together, then we have what is called the general addition rule, which is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. The reason why we have to subtract off the probability of A and B is that if we do not have mutually exclusive events, meaning we have events that can happen together, you're actually double counting the and probability when you add A and B together. We'll see this on the Venn diagram on the next slide in just a minute. If A and B are mutually exclusive, then the probability of A and B will be equal to 0, and this formula will become the same as the addition rule for mutually exclusive events. That's why we call this the general addition rule, because even if you had mutually exclusive events, you could use this bottom formula, but the last term would disappear, and you're really just left with the first formula. Here we can visualize the probability of A and B, which is the intersection of two circles, and the probability of A or B, which is anything that's in either of the two circles. Here is the formula for non-mutually exclusive events, which is what we have here in the picture. Non-mutually exclusive just means there is some overlap between the two circles. Now here's why this formula makes sense. If we take the probability of A, that's kind of like adding up the entire area of the circle A, but that's including the middle part, which is the probability of A and B. If we add up the probability of B, we are like taking the entire area of the circle B. But once again, that also includes the middle part, which is the probability of A and B. We want to include the probability of A and B, but not twice. So if we've added up A and B, we've actually added up this middle part twice. So we need to subtract it off. So that is only counted one time. Let's look at some examples. 60% of students in a stats class are freshmen and 20% are sophomores. Let's say that A represents the students who are freshmen and B represents the students that are sophomores. Are events A and B mutually exclusive? Remember that mutually exclusive events cannot happen at the same time. So can a student be both a freshman and a sophomore at the same time? No, they cannot, which means that these two events are mutually exclusive. A student cannot be both a freshman and a sophomore at the same time. Let's say we are asked, what is the probability that a randomly selected student is either a freshman or a sophomore? Well, since we have mutually exclusive events, we can use the formula for mutually exclusive events. The probability of A or B is equal to the probability of A plus the probability of B. This is kind of like having two non-overlapping circles. If we want to find the area of both circles, we just have to simply add those two circles together, the probability of A plus the probability of B. The probability of A in this case is 60%. 60% of the students are freshmen, and the probability of B is 20%, because 20% are sophomores. Adding those two things together, we get 80%. There's an 80% chance that we randomly select a student, and for that student to be either a freshman or a sophomore. Here's another example. 30% of students in a stats class are business majors, 45% are male, and 10% of students are both business majors and male. Let's let A represent the students who are business majors and B represent the students who are male. Are these two events mutually exclusive? Remember, events are mutually exclusive if they cannot happen at the same time. Well, in this case, these two events can happen at the same time. So that means that the answer is no. A student can be both a business major and a male at the same time, so these are not mutually exclusive events. What is the probability that a randomly selected student is either a business major or male? Well, since we do not have mutually exclusive events, we have to use what is called the general addition rule. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This is like we have overlapping circles, and if we just added these two things together, we'd actually be double counting the overlap, so we need to subtract it. Let's write down the probability statements. 30% are business majors, which is the probability of A, 45% are male, which is the probability of B, and 10% are both, which is the probability of A and B. Therefore, we can find the probability by adding A and B together and subtracting the probability of A and B. So we get 30% plus 45% minus 10%, which is equal to 65%. There is a 65% chance of a randomly selected student being either a business major or male. Let's look at another example. In a classroom, 30% of students are math majors, event M, and 20% are biology majors, event B. 60% of students own their own car, event C. Assume that no students are double majoring in both math and biology, and that owning a car is independent from class major. Let's write down the given information. The probability that someone is a math major is 30%, and the probability that someone is a biology major is 20%. The probability someone owns their own car is 60%. What is the chance a random student is either a math or biology major? Since we are asked an or probability, we must consider whether or not these two events are mutually exclusive or not. These events are mutually exclusive because they tell us that we need to assume that no students are double majoring in both math and biology. So therefore, the probability of M or B is simply the probability of M plus the probability of B, because those two events cannot happen at the same time. Plugging in the numbers, we have the probability of M or B is equal to 0.3 plus 0.2, which is equal to 0.5. There is a 50% chance that a randomly selected student is either a math or biology major. What is the chance that a random student is either a math major or owns their own car? Well, presumably it is possible to both be a math major and own your own car. So we would say that these two events are not mutually exclusive. So the formula is going to be the probability of M or C is equal to the probability of M plus the probability of C minus the probability of M and C. But we don't have the probability of M and C, but we are told that owning a car is independent from class major. Therefore, we can find the probability of M and C by simply multiplying the probability of M times the probability of C, since they are independent events. Multiplying those out, we have 0.3, which is the probability of M, times 0.6, which is the probability of C, which is 0.18. There's an 18% chance that someone is majoring in math and owns their own car. Finally, we need to find the probability of M or C, and we have all three numbers that we need, so we can just plug them in. We have 0.3 plus 0.6 minus the 0.18 that we just found. The answer is 0.72. There is a 72% chance that someone is majoring in math or owns their own car. Alright, so here is a problem for you to try. So pause the video and give it a shot, and I'll be right back to help you out. Alright, I'm assuming that you've given this problem a shot. The problem says that 20% of musicians in a community orchestra are violinists, and 10% are cellists. 40% of the musicians in the orchestra have some formal training in college or university. That's going to be event T for training. And assume that each musician only plays one instrument, and the amount of training is independent of the instrument played. Write out the probability statements for the three probabilities that are given. So we are given that the probability someone is a violinist is 20%, the chance that they are a cellist is 10%, and 40% of them have some musical training, so that would be the chance of T. We are asked, what is the probability a random musician is either a violinist or a cellist? Since we are asked for an OR probability, we have to consider if those two events are mutually exclusive or not. Well, the problem says assume each musician only plays one instrument, so that means that those events are mutually exclusive. They can't happen at the same time. Therefore, the probability of V or C is equal to the probability of V plus the probability of C. Plugging in the numbers, we have 0.2 plus 0.1, which is equal to 0.3. There's a 30% chance that someone either is a violinist or a cellist. The last question is one for you to try. It says, what is the probability a random musician either is a cellist or has some formal music training in college or university? So my hint to you is that these two events, C and T, are not mutually exclusive. You can be both a cellist and have training in college or university. So you'll have to use the appropriate formula for that, which may require that you calculate the probability of C and T. Alright, that's all I had for you in this video, so hopefully you found it useful, and I will see you again in the next one.